Entropy seems to be the law, that we are marching inexorably towards the heat death of the universe. And yet, at the local level, we see order, we see life, we see minerals, we see crystals, we see stars that are pumping out radiation that is used by the life. And so we have this sort of sense that even though at the largest scales, entropy is the rule, at the small scale, there does seem to be a force of order that is going on. Is that something that's just temporary and in the longest time scales, entropy will take over again? Or is there some force that is pushing higher and higher complexity at the local level? My guests today argue that that might be the case. Dr. Robert Hazen and Dr. Mike Wong are scientists at the Carnegie Institution for Science in Washington, D.C. And they have written a new book called Time's Second Arrow: Evolution, Order, and a New Law of Nature. And they argue that this isn't just chance, that it's not a fluke, that there is in fact some kind of drive towards information complexity that is going alongside entropy and the other laws of nature that we're more familiar with, Newton's laws and heat and all of that. And that their observations have even allowed them to be able to make predictions about how various living systems will evolve. Bob is a geologist, studies minerals. Mike is an astrobiologist and studies the origins of life. And so they come together to see how this sort of general trend seems to be playing out time and time again in the universe. So if this is interesting to you, enjoy this conversation about Time's Second Arrow. So this is going to be like a little bit different from the kind of conversations that I normally have. We're going to, this is a Sean Carroll kind of episode, but I'm going to do my best to ask the kinds of questions that I figure Sean Carroll would ask. And I know he has already talked to you. So, hopefully, and I didn't listen to his interview, so hopefully this will work out. So I think, you guys have a new book and you are proposing a sort of a way to explain how there seems to be order in the universe, which is different from the entropy that we all are sadly aware of at all times. Where did this observation start to kind of get into your brains?
Oh, man. You look around us, and you especially think about our universe and the stars and the planets and the galaxies and the structures and these ideas that stars make elements and elements make planets and planets make minerals, and then minerals make life, and then life makes podcasts. We're talking about these things. And it just seems like there is a process in the universe, a universal process of creating order. And so Mike and I and a group of colleagues we got excited about this idea that there seems to be a lawful process that is something that's universal. And we wanted to come up with a way to describe, explain, quantify, and maybe predict how these systems. So I was stuck. I'd been thinking about this for 20 years, and I'm at the end of my career. And this incredibly bright, engaged, dynamic young scientist, Mike Wong, came along and said, hey, let's really tackle this. And he took over. Right, Mike?
Well, yeah, I feel equally lucky to be able to work with you and the rest of our colleagues, Bob. But, especially, we were just talking yesterday over lunch about how you're rethinking classification schemes for how new minerals come into existence. And one thing that I just really appreciate and get inspired by in Bob is his willingness, almost eagerness to rethink things that he has thought before or even has rethought before over and over and over again. And this open-mindedness to trying new ideas and new networks of collaboration is something that I immediately felt like this is the most wonderful thing in the world when I arrived at the Carnegie Institution for Science about 4 years ago. And it led to brand new questions in my mind. I'm an astrobiologist and planetary scientist by training. So trying to understand, how planets evolve and create habitable environments for life, how life might originate on planets, and then how we best go about the project of trying to search for life elsewhere in the universe. But underneath all of that is sort of this fundamental philosophical question of what life is in the first place. And beneath that question is, what is complexity in the first place? Because life is the quintessential complex evolving system, but are there other systems that display other kinds of complexity and evolution, and how is life an extension upon those? And I didn't even realize that those questions were begging to be asked until I fell here into this wonderful network of colleagues at Carnegie that Bob introduced me to.
But I get this question all the time from my audience, and how can you have order on small scales while there is this general tendency towards entropy? And the kind of classic answer that you give is that, at the largest scales, entropy is what dominates, but you can have order on a local level that is kind of borrowing from the larger entropy that must inevitably happen. How is what you're proposing different from that, local order versus global entropy?
So Fraser, it's a very subtle difference. In the past, people have said there's one arrow of time, there's this increase in disorder, increase in entropy, and that drives everything in the universe, including the local pockets of order like living things. And so in that rhetoric, entropy causes evolution. What we say is entropy is completely consistent with evolution. Evolution has to obey the second law of thermodynamics like everything else, but that in fact there is an additional descriptive law that talks about how that order arises. And it's a very mechanistic idea, and it's one that's based not on energy, but on information. So we think it's a second arrow of time, which happens to be that's the title of our book, Time's Second Arrow, because this is kind of a radical, maybe audacious, maybe crazy idea, but it just, thinking about this, that's what we've concluded.
So I guess, what is the evidence? I mean, you think about, say, quantum mechanics, and you have sort of the world split into two groups mainly, sort of thinking about, you have the Copenhagen interpretation versus the many worlds hypothesis, and sort of people and in the end, they're kind of describing the same circumstances, but coming up with a different underlying explanation for it. So, Mike, what do you see as a biologist, an astrobiologist, in the kinds of things that are happening that make you feel like there is some other process that's at play here?
Yeah. So I want everybody to imagine a universe that is very much like our own, started out with a big bang, a state of very, very low entropy, and is evolving toward a state of extremely high entropy. So one leading cosmological model for the end of our universe is something called heat death, where everything just dissipates into thermal equilibrium, and there are no more interesting entities in the universe. And so those are the sort of bookends, but you can imagine a universe that starts off with a big bang, that ends in heat death, but no complexity arises. It just gradually moves towards states of higher and higher entropy without creating all of the marvelous things that Bob listed just a few minutes ago. But that's not the universe that we live in. We live in a universe of increasing complexity, order, patterning, diversity, and information. And so one way to think about how the increase of entropy is decoupled from the increase of information in our world is by thinking about, some everyday examples of processes that increase entropy, but increase information differently. So let me give you an example from my own work. I spend some of my time doing computer coding. And so every time I click a button on my computer to enter a new character into my computer code, I increase the entropy of the universe by a minuscule amount.
Right, a little bit of heat.
A little bit of heat, a little bit of dissipation radiates out into the world, increasing the entropy. It doesn't really matter which button I click. It could be a parentheses with a curve, or it could be a bracket, sort of like with right angles. but only one of those characters will make my code run. The other one won't. And so the reason why we have codes that run efficiently, those that are selected, are because of their function, that they have increased what we call functional information. And both processes of creating codes that don't run and creating codes that do run increase entropy in the universe. Clicking the square bracket versus the parentheses increases the entropy just the same, but only one of them will be selected for its function.
But is that coming from you as the person who is writing the code? I mean, is that just pushing it back one level?
So the question here is then, function, we're talking about selecting for things that work. And yes, indeed, the coder selects for things that work, but so does nature. There are certain configurations of molecules, amino acids and DNA and lipids that just are a blob. They're just a shapeless mass. And there are other configurations of those molecules that, in fact, are a living cell. And nature, it turns out, says, well, the living cell, which has the ability to reproduce and pass information on from one generation to another, is the thing we're going to select for. Now, the entropy in terms of producing those molecules would be the same whether it's a living thing or not. But there is a selection process in the natural world for things that, as Mike has pointed out, do three things.
So we think that there are three fundamental sources of selection. The first is for what we call static persistence. This is the idea that certain entities will maintain their structure, without decaying toward a high entropy state for some time. And we see this in long-lived nuclei as well as in stable crystal structures. Another kind of persistence is what we call dynamic persistence. And this one applies to open systems that are constantly exchanging energy and matter and even information with their environments. And so life is a great example of an open system. So is a star or a hurricane. And in these systems, you can't talk about stable arrangements of matter because they're always, changing the parcels of air for a hurricane or the carbon in the case of life with the environment. But what we can talk about persisting is the activities of these systems. And then in these dynamic systems, you can have systems that discover new functions, new ways of being, new ways of increasing and enhancing their persistence through time. And we see this all over the biological world, the invention of locomotion, of flight, of sight, of smell, things like this that help organisms maintain themselves. So there's this third selection pressure we would say is for novelty generation, this ability to create new ways of being and living.
Right. So you sort of ship of Theseus sort of concept. You're left with it's still the ship, but it's very dynamic in the boards and planks that are coming and going in the thing. But okay, so if obviously. This is a scientific question, and so as scientists, your job is to sort of look for the evidence, and you are describing these sort of large-scale trends that appear to be all around us in the universe and the kinds of things that you see, the patterns that you see. Human beings are wonderful pattern-matching machines. What would be some specific predictions that you might expect to see that would give you much more credence that you're moving in the right direction?
So, Fraser, there are several things that a natural law like we're proposing needs to do. As I mentioned, describe and explain. And we think that just this mechanism of selection is the description and explanation of what happens. But then you need to quantify it, and you need to make predictions. Now, our law suggests that a certain kind of information associated with the function of an organism ratchets up. It continuously increases. So, can we do a quantitative test? Well, we published a paper in the Proceedings of the National Academy a year ago or so, in which we looked at mineral systems. I'm a mineralogist, so we looked at how mineral systems have become increasingly diverse and patterned over the last 4.5 billion years. And indeed, step by step, you always see this increase. The possible configuration space of atoms that make minerals keeps expanding because Earth does new things in mixing in the way certain elements become concentrated. And that space expands much, much faster than the number of stable minerals, which in our formulation means that this information, this functional information increases. So that's one thing, is actually making a prediction and testing it. The other thing is the way that other people will then take our idea, our model for evolution, and applying it. And maybe Mike can tell you about the most dramatic, unexpected, exciting thing, and that's there's a group of cancer researchers that are using this model to predict how tumors evolve.
Right. Yeah, there's this group of oncologists who have started citing our work and have actually gotten in contact with us to work together on applying our theory of evolution by selection for function to tumorigenesis, the way that tumors develop within our bodies. And so, real briefly, tumors, they increase in their complexity and their function, often to very devastating ends, but they don't do so in this classic Darwinian paradigm. The way that Darwin described the evolution of species here on Earth through the heritable variations and common descent. Tumors aren't like that, yet they still display, just like minerals do, this increase in patterning, in order that to themselves help them persist, but then ultimately, extinguish us if we're unlucky. And so in order to better understand how these tumors develop, you can apply this framework of selection for function, where now our bodies will be the environment the tumors are evolving in, and they're evolving to persist better and better against our body's defenses, which we have many, but eventually the tumors can overcome them. And so if we understand these evolutionary trends and cast tumorigenesis in an evolutionary framework, which Darwinian evolution just wasn't fully equipped to do, then we can come up with novel therapies to try to combat these tumors, stifle their evolution, put them in these evolutionary traps where you can cause them to select for functions other than causing us harm. And so this is opening up, I think, a brand new paradigm in how we combat cancers.
That's really interesting. That had never occurred to me, but now that I think about it, that tumors are not a separate species that is evolving, like parasites in lockstep with the bodies that they kill, and yet our bodies haven't crushed them yet. You would think that this would be a relatively simple problem. You see this thing, there's a mutation, you catch all the mutations, and then you're done. But in fact, we still, after all of these hundreds of millions of years, we as living creatures have not been able to track down and get rid of every single tumor that's out there.
Sure. And Fraser, one of the amazing things is it's not just oncology, but we've had people contacting us from Google, talking about AI evolution. We have people talking about language evolution, about the evolution of the internet, about evolution of various social structures. It turns out if you have a valid theory of evolving systems, then it has to apply across the full range of the full spectrum of things, where we see an increase over time in diversity, in patterning, in behavioral ability, and so forth. And this is just something you see over and over and over again in the history of life, in the history of our planet, in abiotic as well as biotic systems. And so what we need to find out, we have to be very humble and recognize that we could be wrong, but the test of this will really be the way it's applied to new levels of understanding of this whole range of complex evolving systems.
So, when you think about it from a geology perspective, and you see the minerals, and you think about how new minerals are being formed in new ways, either through various geologic processes, but also the range of minerals that are being produced by the interaction between life and minerals, right? Do you sort of say, okay, maybe we should find minerals that do this, and then wait for someone to announce that mineral? Have you got a wish list of minerals?
We have. We've done exactly that. There's a field that we're calling somewhat coyly mineral ecology, and we can predict minerals that must exist but just haven't been found yet for a variety of reasons, and some of them are very human. It's easy to find bright blue and green and orange minerals. It's really hard to find the dull gray and white powdery ones. And we've shown mathematically that that there are about 50% of the dull gray powdery ones, things with sodium as the main element, that have not been discovered. But when it comes to copper that makes those beautiful blue and green minerals, we've discovered about 85% of those species. So there's the human element in this, but again, we're as humans, we select the things that are pretty. We select the things that have a nice crystal structure. I mean, this just pervades every aspect of existence in a world, especially a living world.
So, Mike, I want to bring this sort of to the topic that I know a lot of my audience is very interested in, and this is the idea of your astrobiology work, Search for Life Beyond Earth. And there's sort of like two big challenges right now. I mean, I guess there's a million big challenges, but one is this idea of a biosignature, of some way, some absolutely certain way of detecting some chemical gas, whatever, in the atmosphere of another world, or in a sample that you retrieve from the surface of Mars, or whatever. You say unequivocally, this was created by life. How do you sort of think about that search under the framework of thinking about increasing information?
What a wonderful question, Fraser. This is actually the exact reason why I came to Carnegie to work with Bob Hazen and the others here, mainly because I was getting a little bit frustrated, even disillusioned with the state of the art of looking for biosignatures, especially on exoplanets, where we're thinking about trying to look for life through the interpretation of a spectrum from an exoplanet that tells us about one or two molecules that could be in disequilibrium with one another in that planet's atmosphere. And you can think up of all different kinds of what we call false positives for that kind of detection, where the planet, through its own geochemistry or photochemistry, that is the planet's atmosphere interacting with the starlight, causing new kinds of chemicals to react in that atmosphere, could mimic the signatures of metabolism, of life spitting out certain molecules into that atmosphere. And I thought we needed a more holistic approach. And so I came to Carnegie 4 years ago to work on the topologies of atmospheric network chemistry, looking at all the different chemicals in a planetary atmosphere and using network representations where you have hundreds of different nodes representing the different chemical species you find in a planet's atmosphere, all connected by various chemical reactions amongst them. And if you take in that holistic picture and apply the metrics of graph theory and network science to this holistic picture of a planet's atmosphere, you might be able to pick up some interesting trends that hint at complexity, that hint at information content. Now, along the way, I discovered that Bob and his colleagues were thinking about applying very similar frameworks, informatics and data science-based frameworks, to the detection of suites of organic molecules for in situ searches for life. That is, for planets that we are close enough to, those within our solar system, that we can send a rover to pick up a sample and then analyze all the organic chemistry in that sample. And again, we're faced with this conundrum of what exactly is a biosignature, especially when we've learned that a lot of primitive materials in our solar system contain the building blocks of life. So last year, it was announced that this asteroid called Bennu contains the nucleobases and many of the amino acids that we find in living systems. So how do you differentiate between a black sludge from an asteroid that contains all the building blocks of life and a bacterium, which also contains all the building blocks of life? Well, the answer is that the answer is in evolution, right? So the bacterium has been constructed through an evolutionary story that has selected certain building blocks over others because they perform biochemical functions. And so the distributions of those materials has been skewed in the bacterium to a degree that they haven't been in the meteorite or the asteroid, which may contain all of the same basic ingredients, but the distributions of those ingredients have been selected merely for their static persistence, just waiting out there in space for 4.5 billion years for a spacecraft to go pick them up and bring them back to Earth. And so we think that evolutionary selection for function leaves its fingerprints in the distributions of organic molecules, and you'll really only be able to pick this up if you look at it holistically, at the entire suite of organic chemistry in a sample, rather than an individual molecule one at a time.
Yeah, I mean, I think at this point it's pretty clear. You know, you talk to astrobiologists 20 years ago, and they say, boy, when James Webb comes online, we're going to look at a planet, we're going to see the presence of oxygen in the atmosphere, and then that's it, slam dunk, aliens. And now James Webb is here, it is looking at planets, it is detecting a range of chemicals, and we know of abiotic ways to make every single one of those chemicals, and that it's probably going to be the interplay of those chemicals and the complexity in the atmosphere that trends towards life. But the argument that I always make is that, there is a disagreement about whether or not there's phosphine in the atmosphere of Venus, and it's right over there. So, right? Like we can go, we can send spacecraft into its atmosphere. We have the most powerful telescopes on Earth able to analyze it, and it is only, tens of millions of kilometers away from us. Imagine how inconclusive this search is going to be when we're looking at exoplanets on, that are light years away. So, and I think, I've talked to a bunch of other people sort of in the field, and it really feels like in both in situ and in atmospheric that you're taking this very agnostic approach instead. That instead of, okay, am I detecting this chemical, boom, slam dunk? It's more like, am I digging up soup and it looks more complicated? The more complicated it is, the more likely there's life there.
That's a really interesting point. So this is a very fun project. First, it involves collecting huge numbers of samples. I mean, we get people sending us samples of organics that were produced through a Fischer-Tropsch process, and,
that's cool.
and ancient rocks. This is a rock that's like 3.5 billion years old, and it has carbon in it. And I'll tell you, Fraser, I mean, my office is just like a mess if I can do this on these are just a few hundred of the many, many hundreds of samples. Some of them powders, some of them rocks, some of them, dead insects or leaves that we've picked off trees. And we analyzed all these, and what we found just miraculously is that the things that came from life have a particular pattern that's very, very different from the molecules that come from non-living. For example, from carbon-rich meteorites or from those synthetic products that I showed you. Because in meteorites and synthetic this remains that you basically find a range of molecules that are all sort of similar to each other, and they form a continuum, whereas in life it chooses very specific molecules. And even if you fragment them after billions of years of degrading, of decay, the fragment distribution is fundamentally different. And that's what Mike and colleagues, we've been running these things and analyzing and using machine learning, and wow, the results were just amazing.
So Mike, I want you to wrestle with the Fermi Paradox then, because if you're seeing this rise of information on sort of wherever it's appropriate, then that sort of makes the paradox even more difficult, because we really should see evidence of this sort of advancing information complexity everywhere we look. And obviously, we look out into the universe and we see what looks like a wilderness, that there's no evidence that we're anything but alone. Or even, as Hart said in 1975, where are the alien spaceships? Like where are the von Neumann probes who should be already here colonizing the solar system? So is it local to the Earth? Can't be. So it's got to be universal. Where is everybody?
Okay. Wow. That's a big question. And there are so many different avenues to approaching it. I think one thing to make clear is that although we see a trend of increasing functional information across the systems that we have analyzed so far, from minerals to artificial life, and into organic chemistry as well, I don't think the law of increasing functional information tells you much about the speed of that increase and whether or not it should achieve life, intelligence, consciousness, technology, etc., on any particular time scale. So I'm not sure if one should wield the law of increasing functional information in a way to claim that we are in a universe populated by Klingons and Vulcans and etc. But nonetheless, it's a good question. Where is everybody and where are all the alien spaceships? And I feel like the answer probably lies in the idea that we haven't searched very hard yet. I think if you talk to some of the folks who are really invested in the SETI project, the search for extraterrestrial intelligence, they've done some really intriguing calculations that say, if you look at the entire parameter space of the universe and equate that to the volume of Earth's oceans, what we have sampled so far is somewhere between the volume of a hot tub and a swimming pool. And it's like, if you took that volume of water from Earth's oceans and didn't find any fish, should you conclude that there are no fish in Earth's oceans? Well, if you did, you would be completely wrong. So I think we just haven't searched very far yet. But also, casting things back into the lens of information processing, I think one potential reason why we have not found hard evidence for alien civilizations yet is because we just don't know what to look for. Human civilization and the signals that we produce and the signals that we expect when we think about looking for extraterrestrial intelligence, we've only been producing those signals for a very short amount of time. And you think about the history of the evolution of life on Earth, and life, as Bob said, ratcheted up in its complexity, its information, and its also ability to integrate the information about its environment. If you think about a bacterium, it's actually doing some very sophisticated information processing at the micron scale to understand its own local environment, and it can adapt and survive very well there. But could you ask a bacterium to predict the next major transition in evolution to a eukaryotic cell? I don't think, even with all of a bacterium's fancy information processing capabilities, it would be able to make that kind of prediction. Could the simplest eukaryotic cells have predicted a multicellular organism? No, I don't think so. Could a multicellular organism have predicted human society? Not sure about that. So what is it that we cannot predict about the next major transition in evolution? And if we cannot truly predict what that is, are we even looking for the right things when it comes to the question, are we alone in the universe? And that's something that keeps me up at night. In the best possible way.
Yeah. But I guess, like from my perspective, or when I sort of think about this, a lot of times when you say, well, where's everybody? And you gave, one answer, and I have 1,000 sort of counters to that. But that if there is this sort of driving force to informational complexity, then that makes our existence feel less like an incredible chain of events, difficult filters that we were able to pass through. One, blob in a puddle was hit by lightning and you got that abiogenesis. Some clever bacteria consumed another bacteria and you got eukaryotic life. That instead, that life finds a way, that information finds a way, complexity finds a way. And so, you end up with a bacteria colony that is still single cellular organisms, but they have developed emergent intelligence because that's just like, that's what's got its, finger on the scale, is moving us in that direction. And so it feels like one of the predictions you would make is, in fact, we would expect to see just more ways that this increasing information complexity has been, is the force, to use a wrong sci-fi show, I know, and I apologize.
So you're absolutely right. But one of the things we don't know, and that our missing law doesn't tell us about, is how probable or improbable each of those steps is. What we're saying, you select for function amongst all the configurations. So imagine that 1 in every trillion configurations leads to some ratcheting up. Well, over the course of Earth's history, then that's very likely. There's certain minerals that will always form. There are isotopes that would always form in a stellar system, given our universe. But there may be some bottlenecks. And maybe there's some step in complexification going from amino acids to a first peptide that actually does something, a protein or an enzyme that does something useful. Maybe that's not 1 in a trillion, maybe it's 1 in 10 to the 100th, in which case it's not a certainty in our cosmos that you're going to make that leap. You may do it, but it's a matter of statistics or stochastics. And we don't know. We simply don't know what the landscape of function is for some of these critical steps. Now, I would love to think that the landscape is such that on any Earth-like planet given 1 billion years, life's going to emerge. And that if life emerges as a single cell type thing, then eventually it's going to become multicellular. And if it becomes multicellular, then eventually it's going to have society and be able to think about the fact that it exists. But we don't know that. This is now still philosophical speculation. I hope that we can make progress on those questions, but at this point, our law of increasing functional information is agnostic on those points.
Bob, what are you obsessed with right now?
Oh man, Fraser, I am just, my head is exploding because I'm interested in evolving systems. I'm interested as a mineralogist in specifically how minerals have changed through Earth history and how minerals contributed to the origin of life and how life contributed to the origin of minerals. But then that leads to this larger question about, is this a specific example of a general principle, which is our missing law? And then how can we apply the missing law? And then that leads to this idea of the search for life on other worlds. And I think the most exciting thing I've ever done in my life working with Mike is to apply these new theoretical ideas to the search for life through looking for the distinctive pattern of life's molecules. It's a very rigorous, laboratory intensive. I spend hours and hours in a chemical laboratory using nasty chemicals, dissolving rocks. And then Mike takes the residues that I produce that are organic rich, and he runs through the machine. And then our colleague Anirudh does the machine learning on this. And we have these incredible gatherings and meetings, and the opportunities for discovery, I think, are just exploding. So I see this, it's just such an exciting time where all of these ideas are coming together to really answer some of the largest questions that we've faced as humans since humans were first thinking about this kind of thing.
Mike, same question.
I am obsessed with these few words that Bob said to me the other day, and I can't stop thinking about them. He said that your life is your most creative act. And I'm an early career academic, with these short-term postdoctoral gigs that last no more than 2 or 3 years. And I'm still trying to find my, permanent position out there, whether that's a faculty position at some university or maybe a staff scientist position at a place like Carnegie, where I currently work. And thinking about how I am an evolving system myself, and how, you can think about all of these different possibilities, imagine possibility space for yourself and your trajectory, and then try to select the ones that will be the most fruitful. And I've been thinking a lot about my life as a creative act, and, imagining sort of destinations for myself, and coming to realize through inspiration from, Bob and my colleagues and my friends that I talk to and commiserate with sometimes about the difficulties of finding a job in this kind of job market, that, we've always dreamed of our goals being sort of this like fancy job title or position or accolade. But maybe what we really all should just be striving for is a sense of wonderment, of fulfillment, purpose, and just being at peace with ourselves. And so I'm obsessed with trying to find my path toward those feelings and trying to let go and not worry so incessantly about, am I going to land a position at that, prestigious university or whatever, and just trying to live every day getting closer and closer to those feelings.
I get this question a lot as well. People want to sort of know what my plans are for universe today and so on. And I'm like, I have no plans. I just follow my curiosity. Right. That's it. Every day, just what when I look at a paper or when I look at a new book comes in, and I just think, do I want to know more about this? Would you like to know more? I say yes, and then I reach out and do an interview, and that's literally the beginning and the end of my goals in life, is just follow the things that make me they keep me interested and entertained, and then I I make this available so people can watch as I'm doing my process of being a journalist, and somehow they keep wanting to watch. So, the system works. But I think that's exactly right, that, if you continue to be creative, follow your curiosity, then you will make an impact, right? As opposed to trying to sort of win someone else's game. I love it. Well, Bob, Mike, I need to see the book one more time so people can remember and have that burned into their consciousness as they go. Time's Second Arrow, Evolution, Order, and a New Law. Thank you so much, guys. Good luck with finding some kind of bulletproof evidence that you guys are on the right track. And I look forward to the announcement of aliens.
Thank you, Fraser.
All right. Thanks, guys. I hope you enjoyed that conversation with Mike and Bob. Now, Mike is the host of a science fiction podcast called Strange New Worlds. And so I had a bunch of questions about Star Trek and science fiction, and was able to have a longer conversation with them about both the sort of the state of technology and developments in Star Trek, as well as sort of what role Star Trek still has to play in our modern society. And so if you want that larger conversation, we have that over on Patreon. Now, it's available completely for free. You don't have to pay us. You can just click the link in the show notes and go over and watch the longer version of this exact same interview with information about Star Trek as well. Now, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Balak, Cy Nelson, Darkfinger, David Giltonen, David Matz, Evan.Pro, Greg Feely, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Nordspace, OneStepForAnimals.org, Paul Roebuck, Rank Haidu, Richard Williams, Sean Sargent, Stephen Finley-Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldaborg Galactic Defender, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. This was a very interesting conversation for me, a little bit outside of what I normally talk about, but I was able to drag it back into the realm of astrobiology and exoplanetary research, which I hope you enjoyed. Now, if you're interested in that subject, I've had a lot of conversations with scientists about every aspect of this, from abiogenesis through the Great Filter, the Fermi Paradox, talked with Robin Hansen about his concepts of grabby aliens. I've talked to researchers about the study of exoplanetary atmospheres and why this is so difficult. Venus is an analog for exoplanets on Earth, how we are finding chemicals in deep space, a ton of interviews that cover a very similar ground. And so if you're interested in those kinds of topics, we've got lots of interviews. I'm going to put a bunch of links in the show notes to other interviews that I think will be well related to that. All right. Hope you enjoyed. We'll see you next time.